So, let's talk about... Yeah, what's up?
I didn't call my name. I just recently added the course.
Oh, your name?
I'm a friend.
Okay, you sent me the email yesterday, right?
Earlier today. Oh, yes, yesterday.
Okay, I was like... Okay, that sounds... Okay, I thought so. Anyways, just wanted to make sure. Okay, so, for those of you that did the warm-up, so the premise was I asked you to just find the derivative of 2 times 3x plus 4 to the power of 10. So I'm just going to let this equal y. So for those of you that did the warm-up, what did you guys end up with?
I ended up with 60 times the quantity 3x plus 4 to the 9th power.
I like that answer. It's a good answer. So let's talk about it. So basically, the idea is that we have to use chain rule to get the derivative of this thing. Okay? So we have y prime equals, let's see. So this 2 here is just constant, so we can just leave that alone for now. So ultimately, the derivative falls into evaluating this part right here. So we have, let's see, by power rule, we have 10 times 3x plus 4 to the power of 9. But then, because by chain rule, we have to then multiply by the derivative of the inner function, 3x plus 4. But the derivative of that, well, that's just 3. So from this, you can then combine the 2, the 10, and the 3 in terms of multiplication to get 60 times 3x plus 4, all that to the power of 9. Okay? Okay, so that wasn't too bad of a warm-up. Pretty nice, quick little review of Calc 1 stuff. So nothing too crazy. So the thing is that tells us that the derivative of this guy right here is 60 times 3x plus 4 to the power of 9. Now, if we use antiderivative notation and terminology that we discussed last time, we can also express this in a different way as well. So what I mean is the antiderivative of 60 times 3x plus 4 to the power of 9, well, that is going to end up being 2 times 3x plus 4 to the power of 10 plus c, or using actual integration notation, we have 60 times 3x plus 4 to the power of 9 dx is then equal to 2 times 3x plus 4 to the power of 10 plus c. Okay? So, okay, that's all good and all. So that gives us a pretty nice way to evaluate this integral. But let's say for the sake of the lesson that we did not have this original function to begin with, and we instead were just focusing solely on this. So what I mean is that what that says is, okay, how do we find this answer if we just start with this? But how to find antiderivative in starting with if we start with the integral 60 times 3x plus 4 to the power of 9 dx. So if we just start with this, then how do we get back to our original function from the warm-up? Well, that's where our good old new technique, substitution, is going to come into play. Okay. So I did this in the 1130 section, but I'll do this again. So before I get any further, so this is the thing you'll need to do. Before I do that, I should probably address these two things. Quiz 1 is going to be next Monday, covering lesson R at the end of lecture. And quiz 2 is going to be covering lessons 1A and 1B, covering that next Friday at the end of lecture. So you'll get some reminders of quiz 2 throughout the week, but make sure to keep quiz 1 in mind for next Monday. But it should be a pretty quick little review of Calc 1 stuff, so it's not going to be too crazy. But just keep that in mind for the weekend. Anyways, back to the actual lecture. So the idea behind substitution is basically, as the warm-up alluded to, we basically are sort of undoing chain rule here. So undo chain rule. Okay? So basically the idea is, the most general way I can express this idea is that we're basically introducing this dummy variable u that we are basically letting equal the inside of some other function. So to give you an idea of what I mean by this, so consider expression inside the power of 9 in this expression here, in this integral. So in this case, if we focus on this 3x plus 4, so i.e. 3x plus 4, then what we're going to do is that we're going to let this dummy variable u that I just mentioned be equal to that, this expression here. And let's u equal 3x plus 4. Now, the reason we're doing this is we're basically going to then say, all right, well, then what we're going to do with this is then we're going to take the derivative of this thing and work with that. So if I then take the derivative of u with respect to x, then what would the derivative of this thing be? So if u equals 3x plus 4, then what is the derivative of that with respect to x? Yeah, it's just 3, right? Okay. So that gives us that, but another way I'm going to write this, and because we'll need this for our problems, is we have du equals 3 times dx. Okay? Okay, and I'm going to box this in because this will be important. So how did I write this in the last section? Okay. So we'll use this form with substitution. Okay. Okay. So now what we're going to do with this is now we're going to solve for dx from this. Okay. So now solve for dx. Okay. So in this case, it plays pretty nice, so you just divide by 3d at the other side, no problem. So we have dx, in this case, equals du over 3. Okay? So here's what this yields us. So if we rewrite our original integral, 60 times 3x plus 4 to the power of 9 dx, then what we end up with is, well, let's see. So 60, so nothing changes there. Then we have 3x plus 4, which we are letting equal u. So we have u to the power of 9, and then dx, which is du over 3. du over 3. So here's what happens from this. So let's go ahead and clean this up and see what happens. So we have 60 over 3, well, that's 20. That's not too crazy. So we have 20 times u to the 9th, and then du. Okay? Now, the reason why I did all this is because now you'll notice that this entire integral is now in terms of u and du. There's no x or dx. And that's going to be the key thing when we do these types of problems. So no x or dx. We need only u and du. Okay? Okay? So, now that we have this in mind, we can now take the antiderivative of 20 times u to the 9th with respect to u. So, at this point, this basically boils back down to a Calc 1 antiderivative. So, with this in mind, and we use the antiderivative power rule, what should we end up with as our antiderivative with respect to u? Plus Good, okay. So what happens is that we then apply our antiderivative power rule. So this is 20 times u to the 10th over 10 plus c. So this simplifies to, well, 2 times u to the 10th plus c. But then we realized, well, wait a minute, the original function, well, the original integral rather, was in terms of x, so that should probably indicate that our final answer must also be in terms of x. So let's go ahead and do that. So we have 3x plus 4 to the power of 10 plus c. So this will be our final answer and is thankfully consistent with what we've established above. So, okay. And I'll go ahead and write that down as well. So original integral in terms of x. So answer must be in terms of x. Okay. So that's basically the idea with these types of problems. So if we just have like an indefinite integral that involves substitution, we will need to make sure we put everything back in terms of the original variable. Okay. Okay. So that's all I really wanted to say on at least this specific example. So any questions on that? All right. So one note before we move on to the second page. So notes for substitution problems where a linear function, so something like mx plus b or mt plus b, is quote-unquote inside another function so something like cosine of 3x plus 2, e to the negative x, etc. Let u equal the linear function. Okay. Okay. So just one important thing to keep in mind for these types of problems. Okay. So any questions on that note before we move on to example, well, the actual first example? Okay, so I'll give you guys a second to write that down. Does anyone still need to write the first page down? Okay, I'm going to take lack of yes to be no, so I'll go ahead and take this off. Alright. So, let's look at example 1. So, now we have to evaluate this integral of x squared times the square root of 31 minus 5x cubed. So, well, this is definitely not a linear function, so we're going to have to be a bit more general in our approach here. So in this case, so what are we going to let u equal here? So what is u equal to here? So in this more general setting, so choose parts of expression inside integral whose derivative equals a constant multiple of another parts in more general setting. So in the more general setting where we don't have a linear polynomial inside another function, that's the general rule of thumb that you're going to have to utilize for these types of problems. So, here's one thing to note. So just to help give you guys an idea of what to look out for with these types of problems, then let's go ahead and take a look at 31 minus 5x cubed. So if we take the derivative of this guy, using the power rule for derivatives, then what would the what would the derivative of this thing be? Yeah, it's negative 15x squared, right? Negative 15x squared, but you realize, well, wait a minute, that's a constant multiple of this thing, right? That's this x squared hanging outside. So, this is going to be a constant multiple of x squared. Okay? So, because of that, that should be a pretty good indication that you should let u equal 31 minus 5x cubed in this case. So let's u equal 31 minus 5x cubed. So then that should imply that du is then, well, as we just established, negative 15x squared dx. So then, as in the last example we did on page 1, that should tell you that if we solve for dx, as we did there, all we really have to do is just divide this part over to the other side. So we have du over negative 15x squared. Alright? So then, what are the consequences of this? So, more specifically, why do we need to make sure that this du, this expression here, is a constant multiple of something else inside the integral? Well, let's take a look at that, shall we? Because if we do, then we have, well, x squared times square root of 31 minus 5x cubed dx. So that's going to equal, well, x squared times the square root of, well, 31 minus 5x cubed, which we are letting equal u here. And then dx, which is then du over negative 15x squared. Okay? Now, here's why this constant multiple of another part of the integral is so important. Because you'll notice these x squareds here, they just go away. And now you're just left with some constants times something in terms of both u and du. So, to put this in a cleaner manner, we have negative 1 over 15, then times the square root of u, or u to the 1/2, du. Okay, so now that we have that, so this integral in terms of both u and du, now let's go ahead and apply the antiderivative power rule again on this thing. So if we do that, we end up with, well, negative 1 over 15 times what?
2/3.
Yeah. Okay, well, 2/3.
Thirds, u to the 3/2 power.
Yep, 3/2 power.
Du.
Well, du is, well, we already did the antiderivative, so we don't need du, but we need
Plus c.
plus c. Good. Okay. So then from this, we say, all right, let's go ahead and combine these two fractions together. So since they're just multiply, we just go ahead and multiply the numerators together and then the denominators together separately. So we have negative 2 over 45, and then times u, which in this case is 31 minus 5x cubed to the power of 3/2, and then plus c. Okay? So that will be your final answer for example 1, that you would put in long cap. Alright? So, any questions on that example? Alright, cool. So yay, nay, somewhere in between? Alright? Okay. So yeah, some of these problems are kind of tricky, but once you get the general gist of it, it makes a lot more sense. It just takes a lot of practice to get these types of problems down. But thankfully, the second problem will be a lot nicer in terms of the computations. So at first it seems a bit daunting because if we take a look at this, we have to evaluate each of the quantity x plus e to the x. So it looks like we have an exponential within an exponential, which definitely looks scary at first, but it looks less daunting if we manipulate it before we do any actual substitutions. So here's what I mean. So we have e to the x plus e to the x dx. So what I'm going to do is I'm going to manipulate this expression here before we move on. So what I'm going to do is I'm actually going to break this up into the product of two things. So if we use the appropriate exponential law, so if we recall, if we focus on the more general rule, then we can break up this e to the a plus b thing as a product of what two things from exponential laws? Yeah, e to the power of a times e to the power of b, right? That's just one of the exponential rules that we should be familiar with. So, using that, we can break this up as e to the x times e to the power of e to the x dx, right? So, using this way to express the integral here, and recalling the rule for choosing u, then what would be a good way to express u here? Any thoughts, comments, or suggestions? What would be our u variable here? What's that? Well, not quite. But you do notice that e to the power of x here is embedded within another e to the x, right? And you notice, well, wait a minute, the derivative of e to the x is itself, which is right here, right? So, taking that q into account, what do you think u should then be? E to the x. Good. So, e to the x should be equal to u here. So then, as I said, then du will then be equal to e to the x dx. And then as a result, if we then solve for dx in this case, we have dx is equal to du over e to the x. Okay. So now that we have that, we then say, all right, so e to the x, well, that's just, well, I'll leave it here for now, and you'll see why in a second. We have e to the x, and then times e to the u, and then times, well, du over e to the x. Because then you realize, well, wait a minute, these e to the x's cancel each other out fairly nicely. So ultimately, you're just left with e to the u du. Okay? And then noting the correct antiderivative for e to the u, what would this then equal? So the antiderivative of e to the u with respect to u should be what? Well, e to the u, there you go, plus c. E to the u plus c. Okay? And then we need to make sure our original variables incorporated into our final answers. So noting that u is equal to e to the x, we have e to the power of e to the x plus c then becomes our final answer. Okay? So definitely a lot cleaner than example 1, that's for sure. So thoughts on this? Good, nay, somewhere in between? All right. Okay, I'm seeing a few sideways thumbs up. What's okay? So let's see. So does anyone need page 2 before I move on? Okay. All right. So moving on to page 3. Let's look at example 3. So we have to find the function x whose tangent line has slope tangent of x, for x in the domain of tangent, and whose graph passes through the point 2 pi comma 6. So one thing to note here is that we're going to have to use, they're you're using tangent of x for this slope function. So before we move on to proper computations, let's go ahead and recall something. So if we recall, the derivative f prime of x, if you recall from Calc 1, this is supposed to help give you the slope of the function f of x at any given point. So this gives a slope of f of x at x. Okay? So here's what this says. Using this reasoning, that means we're given two things. We're given the derivative of some function whose tangent line has slope tangent of x. So that says that this tangent of x function helps give us the slope at any point. So utilizing this reasoning and this piece of logic here, what should that tell you about what f prime equals in this context? It's just tangent of x, right? So we're given f prime is tangent of x, and we're also given a specific point on this line, or the original function. So we're given a point on the original function. So if we treat this point as something of the form x comma y, we have f of, in this case, let x equal 2 pi, and you should end up with 6 out of this, right? Okay? So that says, all right, we're given a function whose derivative is this, and we're given initial data points, or just some data point, right? Which looks an awful lot like those initial value problems you saw in Calc 1, right? So, all the problem now asks us to do is just figure out, well, what is this f of x function? Find f of x from this. 1 second. It worked. Sorry, I've been talking for too long. I need a drink of water there. Anyways, back to the problem. So as per with these initial value problems that we also discussed in lesson R, the first thing we need to do is we got to figure out, well, what is the general solution to this thing? So first, find general solution. Okay. So we have f of x, so that means we got to find the antiderivative of f prime of x to get the general solution. So recalling that, well, f prime is just tangent of x in this case. So at this point, you're like, okay, well, it's not immediately obvious what we're supposed to be doing here. Like, I know the title of the lesson says integration by substitution, but looking at the integral like that, it's not immediately obvious what to work with here. But it might be a little bit clearer if we rewrite the tangent function as the quotient of what two other trigonometric functions? Sine and cosine, right? So rewriting tangent as sine over cosine, it might now be a bit clearer to see what the use substitution we need is. So any thoughts or suggestions on what you want to let that equal here?
Probably cosine will equal u, since it would technically be to the negative first power.
Yeah. Yeah, and the thing is that cosine ends up being the correct one, but for the sake of working with, just make sure we know why cosine is the one we should be working with. Let's suppose we pick sine, just for the sake of picking, just to see what happens. So if we let u equal sine of x, then that means du is then equal to cosine of x dx, or that dx is then equal to, well, if we divide cosine over to the other side, then we have du over cosine of x. Okay? So here's what happens with this. so if we do all the substitutions that we did before, we then end up with, well, we have sine of x, which is u on top, and then we have cosine of x on bottom, and then dx is then equal to du over cosine of x. But, oh, wait a minute. Problem is now is that there's not really a good way to get rid of this cosine of x now, isn't there? So that should pretty quickly tell you that the substitution sine of x is no good. Okay? So as a result, so pitch this idea and instead do its work with cosine. Because as you'll see, things actually play a lot more nicely with cosine of x. Okay? So we know, all right, so the derivative of cosine, as we saw last time, is equal to what? Negative sine, good. Okay. So then if we go ahead and divide both sides by negative sine, we end up with dx is equal to du over negative sine of x. Okay. So as a result, now let's go ahead and put everything in and see what happens. So we have sine of x over, in this case, u, because that's cosine of x now, and then times dx, which is du over negative sine of x. Okay? And then you realize, well, wait a minute. These sines of x's cancel each other out fairly nicely. So as a result, we then end up with, well, negative 1 over u d. Make this more like an actual u, and then we'll actually move on. But, so, now that we have this, we can note that the derivative of 1 over u, as we saw last time, or in Calc 1, should be equal to what? Natural log of... There's one extra thing you're missing. Yeah, we need the absolute value, right? That's what I was trying to get at. But yeah, we do need plus c, but yes, but we also need the absolute value. So what I mean is that we have natural log of the absolute value of u plus c. Okay? Right? So then put everything back in terms of x, because that's our original variable. And then we have negative natural log of cosine of x, because that's u, plus c. And this is the general solution. So now that we have this, let's say, all right, now that we have that the general solution is f of x equals negative natural log of the absolute value of cosine of x plus c. Now let's go ahead and use this initial data point that we have to get the actual value of c here. Okay? So if we let x equal 2 pi, then we have negative natural log of the absolute value of cosine of 2 pi plus c. So if we harken back to our good old unit circle here, then what is 2 pi? What does cosine of 2 pi equal to?
0.
Not 0. 1, right. So we have negative natural log of, in this case, just 1 plus c. And then, of course, natural log of 1 is 0. Good. So this just goes away. So then we have equal to c. And then by our assumptions, this is just equal to 6, right? So just taking this assumption here, and then we're laying that all equals 6. So now we have the exact value of c. So now this gives us the particular solution that f of x equals the negative of natural log of the absolute value of cosine of x plus 6. All right? And that's the particular solution we need for this problem. And that's example 3 in general. Okay? So, any questions? Good? Nay? Somewhere in between? Alright. Cool. So, let's look at example 4 now. Since now I've got 15 minutes to do this, so we got plenty of time. So does anyone still need page 3 at all? Yeah. So just a heads up, if I don't hear yes, I'm going to take that as no, and I'm going to move on. So just heads up on that. Okay. So moving on to example 4, the last one of the day. So the premise now is that suppose a microwave heats a brownie in such a way that the temperature of the brownie increases at the rate of 54T squared times e to the negative 3T cubed. And this is in degrees Fahrenheit per minute. So the premise states that if the brownie has temperature 30 degrees going in to the microwave, so we can treat that as our initial temperature, keep that word initial in mind. How long should the microwave heat the brownie so that the brownie has 33 degrees Fahrenheit temperature? Okay, so in this case, what we're going to do is now we're going to say, all right, as per the problem's notation, we're going to let capital T of little t denote the temperature function at time t in degrees Fahrenheit. Okay. So, as per what I said about this problem statement here, the problem states that we're assuming that that the brownie has an initial temperature of 30 degrees going in. So, that basically gives us that we have a specific temperature at a specific point in time. So, that says that we're saying that the temperature is 30 degrees at what value T? 0, right? So the reason why I kept the word initial in mind is because if you see the word initial, usually treat that to mean T equals 0. Okay? So now that we have that, and on top of that, we still have T prime of T is equal to, well, this guy right here. Okay. So I'm just going to cheat and do this. So again, it looks like we got another initial value problem now, don't we? So using similar mathematical reasoning as in the last example, we can then find big T of little t. But if you take another look at the problem, you realize, well, wait a minute, that's not what the problem wants us to find, is it? It says, how long should the microwave heat the brownie so the brownie has temperature 33 degrees? So that tells us once we find big T of little t, then that means we need to take our temperature function and then do what with it?
Integrate from 30 to 33?
Not quite. So remember, 30 to 33 degrees both correspond to temperature values. So we need to figure out what value, at what time would the temperature is 33 degrees, right? Essentially. So then what should we do with our temperature function after that? Once we find it. Exactly. Okay? So then basically, now we have a roadmap to figure out where we're going. So now that we have this, that's probably one of the biggest things we need to make sure we know what we're doing going into these problems. Especially with these wordy problems like this, it's good to know, all right, what am I supposed to do? What am I supposed to do, and how do I get there? That's like the good roadmap to figure out what we need to do. Okay? And thankfully, we have enough data to do that, so let's go ahead and roll up our sleeves and get started. So, as per the last example, well, we first got to find the general solution. So, let's go ahead and integrate the derivative of our temperature function that the problem gives us. So the problem states that, well, T prime of T is equal to this guy right here, so that's 54T squared times e to the negative 3T cubed dt. Okay? Now, at this point, you probably have a good enough idea of what will be an appropriate choice for you. So, raise your hand if you have a good idea of what we should let u equal in this case. I wanna pick on someone that I haven't picked on before. Go ahead.
-3 dt.
Exactly. Good. Okay. So then, in this case, if we do that, then du ends up being what? Yep, -9t squared times, well, in this case dt. But yeah, that right idea. So 9t squared dt. So then if we then solve for dt in this case, because that's our input variable, then we have du over -9t squared. So, taking that into account, we then say, all right, we got 54 t squared times e to the, in this case u, because that's our -3t cubed expression now. And then we have dt, which is then du over -9t squared. Okay? So then these t squareds, they cancel out fairly nicely. And we're just now left with -6 e to the u d. Because 54 over -9 is -6. Okay? So, as a result of this, the antiderivative of this should then be what? With respect to u? There you go. Good. -6 e to the u plus c. And then, again, make sure to keep your final answer in terms of the original variable. So we have -6 e to the -3t cubed plus c. So that will be your general solution for big T of little t. So now that we have that, we now use our initial data, the initial temperature equaling 30, to get what C is in this case. So, this is our big T of little t. We then say, all right, well, if we let t equal 0 now, then if we let t equal 0 in just this, what happens? So what does this whole expression here simplify to if we let t equal 0 from this? So if we let t equal 0 in here, what happens? Yeah, c equals 36, right? So if we let t equal 0 here, we end up with -6 times e to the 0 plus c, or just, but e to the 0 is just 1, so we have -6 plus c. So in setting that equal to 30, as per our initial assumptions, then you should be able to pretty quickly get that c is then equal to 36. And then the particular solution, and thus the temperature function we need, is then -6 e to the -3t cubed plus c. Oh, sorry, not plus c. But, which, yes, but that's equal to 36. Alright, cool. So, that's the particular solution. Now, as we just discussed, now we figured out big T of little t, okay, done. But now we also got to figure out what this equation gives us. So if we set big T of little t equal to 33, let's see what happens. So if we set big T of little t equal to 33, then we end up with, well, -6 e to the -3t cubed plus 36. Okay. So why don't you guys take a second, since we got about 5 minutes, why don't you guys solve for the exact value of t? Take a few minutes to do that. We'll deal with the decimal approximation in a second. And see if you can use a one-line calculator if you have it. If not, that's fine, but just make sure you get in the habit of it for the next few lectures. See, a lot of people have their calculators out, so does anyone have the exact value that we need here? So before we start plugging stuff into a calculator, can we at least have a consensus on what the exact value should be? Yeah?
I got the cube root of the natural log of 1/2 divided by 3.
Close. I think you're missing a negative, I think.
Oh, negative natural log.
Yeah. Okay, so let's go over that right quick. So first off, if we solve for the exponential here, then a quick bit of adding or subtracting 36 over to the other side, divide by -6, and you should end up with 1/2 equals e to the -3t cubed. Okay. And then if you take the natural log of both sides, you should end up with natural log of 1/2 equals -3t cubed. So then, if you go ahead and solve for t from this, you should end up with t equals the cube root of natural log of 1/2 over -3. Okay? So what you'll notice from this is that if you plug this into a calculator, you'll notice that this is going to be, well, about 0.61362227. Which you might think, okay, that's kind of a weird small number, but okay. But one thing to keep in mind for this is that, remember, if we look back at the units of the original problem, then, please scroll back up a bit. Okay, a little more. All right, well, whatever. So if we go back to the original problem, there's a big key here to tell us what the units should be. So remember, T prime of T says that it's in degrees Fahrenheit per minute. So that will give you a really good indication here that T has to be in minutes. So, okay. So then going back down here, we then notice, all right, so that gives us minutes, but there's a possibility that the problem could be asking for the final answer in seconds. So in the event that that happens, well, what would we have to do with this answer here to convert this into seconds? Then multiply by 60, right. So if you do that, then you should end up with approximately 36.8. I know the problem said round to the nearest hundredth, but but that's a basic idea. So just multiply by 60, and that will give you the corresponding answer in seconds. And that's about 36.8. So. Okay, so just in case the homework gives you a curveball like that, now you know how to respond to it. So yeah, basically the big idea is watch out for units. That's the big idea. Okay. All right. So other than that, if you guys have no other questions, then I will see you on Monday when we have our first quiz and continue more on our journey through new substitution.